Hannes, and I want to present that joint work with David. So let's get started. So first of all, why would I do that? Well, the current status, or the state at the beginning of this year was, we have the Mirage operating system run by University of Cambridge, which uses OCAML. It is nice, it is memory safe, it is abstract, it uses a lot of modularity features and so on. But for security code, we should call into OpenSSL bindings or say? Well, I wasn't too convinced of that because, I mean, I don't want to call any insecure C code or any C code at all. I actually claim that each line of C code in an operating system is at least one line too much. So, what is our motivation? So, I was here at the beach in Morocco, in Mirlev, together with David, and we thought, well, let's get some code running. So, we have the protocol logic of transport layer security encapsulated in a declarative functional core. The side effects are isolated in front ends, and we claim to have a concise and useful and well-designed API. Well, this is in comparison to OpenSSL, so I mean, well-designed API is at least easy in that. But now let's talk a bit about transport layer security, what it is. It is a cryptographically secure channel between two nodes using TCP/IP. So there's a version in TCP called TLS, and then for UDP there's DTLS, which is the datagram TLS. I think it is the most widely used security protocol since over 15 years on the internet. It is actually a protocol family, so it started out by Netscape using SSL version 1 and 2, which never got public, which is, I think, a good thing. Then we have SSL version 3, also developed by Netscape. And then we have a rename from SSL, from secure socket layer, to TLS, transport layer security. That only has political reasons, because I think that Microsoft didn't want to implement anything done by Netscape. But TLS is now standardized by ITF. Well, standardized, I mean, they write those RFC documents. TLS itself is agile. It has algorithmic agility. So it negotiates actually the protocol version, to speak in the session, the key exchange, the symmetric cipher, and the hash. Oh, and it also uses a lot of old stuff from the telecommunications perspective. So it uses X509 and an ASN1 encoding for certificates. A few details here more. I mean, the properties it wants to establish is authentication between the client and the server. Most of the cases, only the server is authenticated, but you also can do mutual authentication. Then secrecy, integrity, confidentiality. Forward secrecy if you use ephemeral, Diffie-Hellman key exchange, and so on. So it depends a bit what security properties you actually have. It is actually divided into sub-protocols. So you have a record layer protocol, and then you have a handshake protocol, the change cipher spec protocol, an alert protocol, an application data protocol. So application data is which is actually interesting for application developers, because that's where your data is. And then you have a heartbeat sub-protocol, which is mainly used in DTLS. So since we haven't implemented DTLS, we don't have implemented heartbeat yet. Authentication, well, how do you establish authentication? You have two nodes, and at least one of the nodes needs to be authenticated, or should be authenticated. If the server should be authenticated, it provides a certificate via the active session. So it passes a certificate to the client, and the client has a set of trust anchors, which are also certificates, CA certificates, and then it tries to verify cryptographically that there's a signature on the server certificate which is done by any of those trust anchors. Well, and you don't have only a CA certificate and a server certificate, but you have an maybe infinite chain of certificates in between. Well, hopefully not infinite. Handshake. Oh, I wanted to show you live. Let's go here. So this is a local server running on this laptop, as you can see. And it uses actually our OCAML-TLS stack. So it runs OCAML-Kit and co-HTTP. And what you see here is a sequence diagram of the handshake which has just happened between my web browser and the server implementation. And you see there are some messages which are passed on. So the client first initiates the communication by sending a client hello. The server answers where it proposes which different algorithms, which cipher seeds you use. And it also has a nonce, it's random in here and so on. The server answers with a server hello, where it decides on a version to speak. Here it's TLS 1.2. Then it also has a unique nonce server random. Then the server also decides which cipher seed to speak here. So this here is an ephemeral Diffie-Hellman with RSA certificates and AS256 and using CBC mode, and then using as the hash algorithm. So for authentication it uses SHA, so for HANDSHAKE. Then the server sends its certificate. If you can read ASN1, can anyone read ASN1? Well, that is a sequence here, the 30, then 82, well, I will spare you the details. The server also sends in the ephemeral Diffie-Hellman key exchange, in the ephemeral Diffie-Hellman thing, the server decides on the Diffie-Hellman parameters. So this is the Diffie-Hellman group and public and the Diffie-Hellman group and the generator and the public. Then the server sends a server hello done, and the client starts or sends its Diffie-Hellman shared. And then they negotiated basically a master secret which is only known to the server and the client. And master secret is then used to derive the symmetry keys. Then we have this change cipherspec protocol, and the change cipherspec basically says, oh, the next from here on, please use now the negotiated keys and the negotiated algorithms in order to secure the connection. So first the client sends a change cipherspec, then the server sends back a change cipherspec. And now you can see the finished message is the first one, which is actually encrypted. And you can also see that in that diagram because it uses here solid lines instead of dashed lines. And the finished message is rather small. It just contains a hash of all the previous handshake messages in order to authenticate that the handshake was properly done and both parties have seen the very same handshake. And then the server also sends a finished message. Afterwards, application data is actually sent, and we can see here that the client did a GET request and HTTP request. TLS also specifies to renegotiate, which basically handles out new keys. And you can see that here is a hello request, and if I now reload the page, I should see also the So the problem here is that that web browsers usually have multiple sessions towards the server. That's why I don't see all the time all the sessions. But here you can see that there's another session going on. So actually the rekeying has happened. Okay, let's go back here. What happened this year also? So we started the development in February, and it seems to be a good time to start TLS development because in March we had Apple's go to fail, then later this year we had an OpenSSL heartbleed, Then we had changed cipher suite messages, and yeah, nevertheless we have some timing attacks. There's some statistics about the OCAML-TLS. The code size is roughly 10,000 lines of code. Compared to that, some other implementations are a bit more. We have interoperability, so our demonstration server served over 50,000 sessions, so it seems to work out pretty nicely. We had to fix 1 or 2 bugs where we were a bit too strict. We have some missing features like client authentication, session resumption, and ECC cipher speed, so that's elliptic curve cryptography. Performance is a bit slower than OpenSSL, but most time is spent in C, in our C course, so we have actually implemented also a crypto library, and that calls to some C code. In the future, we want soon to have another release, get some more performance, have some comprehensive test suites, implement the missing features, and finish to port Mirage directly onto Xen. And hopefully being able to establish trust in our implementation. So I ask all of you to just read the code and comment and ask us questions about that. Conclusion, well, other people write bindings in 3 months. We just re-implement whole TLS in 3 months. We use OCAML, which is a modular functional programming language to encapsulate the protocol logic. We have 2 different front ends, which is Mirage and LWT. We developed also a crypto library called NoCrypto, ASN1 combinator library, and X509 libraries, and TLS. It's all available on OPAM. It's all BSD licensed code. And we wrote a larger blog series on the Open Mirage project. And it actually also works on that board here. I can briefly show you that if you want. But I'm also happy to ask to answer questions. Are there any questions? So I'm creating here a virtual machine, which is just 2 megabytes big, and then I have here at least some signal on my small ARM board, where it runs without any libc and without any strings connected. It's just a pure OCaml and a pure Mirage OS.
So, how are you going to convince to use that?
I think I convinced the University of Cambridge to use it. Especially that research group over there. I'm mainly interested in using it myself for my mail servers and name servers and whatever.
By the way, we got the guys who discovered Heartbleed. They were working with Citrix to probe Xen server, put it up on, and they ran 2 weeks worth of fuzz tests against the stack, and they managed to crash Linux. 5 bugs in our Unix binding, but never took down the TLS stack itself. So it's been through a lot of professional security pen tests as well. So obviously no formal guarantees, but pretty good.
When can we use your code with QHTTP?
Sorry?
Can we use your code with QHTTP already?
Well, we in theory, yes. So I mean, it works here, like here in practice as well. But I think the integration needs to have some more work.
Yes, sorry, there is a pull request. I just haven't had time to merge it because I'm giving all these talks. As soon as I'm done, I'm going to merge it all. So we should be able to use it with QHTTP on Unix without any of the Mirage libraries, or obviously Mirage as well. It's all fucking right.
Do you have any ideas towards what you can do to address the performance gap?
Yes, so we rewrote the bindings for our crypto library, and then we want to replace the C course, because I mean most time is spent in there, so we want to replace that. And then for AES, for example, we want to use the CPU features like the ASNE, the native assembly instructions. So we have some plans there. Just at the moment, we didn't have time to do that.
What's your timing story? So that there are a lot of timing attacks against SSL. I imagine with the garbage collected language, you might introduce.
So the timing story is rather intricate. So the best practices or the practices used by OpenSSL is to not use any data-dependent branches and not using any data-dependent things at all, and use the same memory access patterns and so on. And we try to do the same, and furthermore, we don't do any data-dependent allocations. But I'm more into trying to come up with a language-based timing mitigation, just as write a DSL which only allows us to do constant time operations on the input data.
Did you have a look at this NITLS code implementation done by the people in the Prosecco team in Paris? You had a reference implementation which is verified. Did you try to use that as a reference for your implementation?
So we talk every now and then with those people. They have implemented it in F7 and F#, which is a bit different from OCAML. And
not too much.
Huh?
Not too much. It's not as
well, I can't compile it on my computer. There is a big difference. But yeah, we are in contact with them and try to collaborate with them. And I mean, I'm envy of them because they have actually formal proofs of the correctness or of the security. But they also don't have the timing stuff, similar to us.
It's just worth pointing out, by the way, the devil's in the details when it comes to these stats. So we have talked about a lot about they don't have, for example, a good ASM1 combinator story, whereas we have a full stack there. So they actually look very complementary. But from a formal perspective, we want to build a spec of all allowable SSL behaviors. What they have is a spec of one particular implementation. So even from a formal specification perspective, they're just quite different. And then obviously this stack is much more modular. So F# is a different modularity story, which is working with Mirage. So the details matter a lot with this stuff. But it's great that we have two independent implementations that are under the virtualized system.
You have tests for signatures? So you don't avoid the go-to fail flag?
Sorry?
Do you have, what's the test suit story, I guess? Right, like go-to fail could have presumably been caught if you had some reasonable tests to make sure that you're not just signing crap. But, all right. So what are you guys doing about tests?
Well, we have some test suites, but we want to automatically generate a comprehensive test suite and run it also against other TLS implementations in order to find out that we have at least the same behavior or a consensus behavior.